Okay. So the title of our work is From Voice to Code, a RAGenhanced pipeline for robust multi-accent order processing. The authors are me, Taha, Pelin Angin Ulkuer, and Merih Angin. It's a collaborative work between Middle East Technical University and Koç University. The rapid revolution of large language models has created significant new opportunities for human-AI interaction, especially through automatic speech recognition, or ASR in short. Our research dives into a specific high-impact application, processing spoken orders in environments like restaurants, as our case study. We aim to bridge the gap between the advancement in ASR and the persistent real-world challenges that still hinder accuracy. So this is our presentation outline. We will begin with introduction and our motivation to this project. Then we will go over our methodology, performance evaluation, and finally our conclusion. The research is divided into two parts. The second part is mostly about RAG, which after a few slides, I will ask my co-author, Taha, to continue with the presentation. So let's talk about the challenge, real-world spoken orders. As voice-driven technologies become more integral to our daily lives, the need for sophisticated ASR and NLP systems has grown. For example, systems that can accurately transcribe spoken language into structured data, such as the JSON format, are critical for applications like order processing in food delivery services and customer service call centers. Traditionally, this task was framed as an information extraction problem known as slot filling problem, where the goal was to identify and extract key data points from a user's request. However, despite incredible progress, ASR systems still face significant challenges in real-world scenarios, such as the restaurant that we mentioned. The core problems we focus on this paper are the complexities that make automation so difficult, which includes, but not limited to, diverse accent, which it has been a long issue in ASR robustness, background noise, which is the real-world acoustic variability in major hurdle, and varied speech patterns. This includes differences in speech rate, tone, and even speaker demographics like gender, age, which can, of course, impact performance. Now, these factors can prevent us from having a reliable automation and ASR model in general. So what did we come up as our solution to address these challenges? We introduced and assessed a complete end-to-end pipeline designed to transcribe and structure multi-accent spoken orders directly into JSON, while maintaining high performance even in noisy settings. The advent of large-scale, weakly supervised models like Whisper by OpenAI has marked a paradigm shift in ASR, showing remarkable zero-shot performance that makes it strong baseline. Similarly, instruction-tuned models like FLAN-T5 and Gemma, both open source from Google, have enabled a text-to-text formulation, simplifying the pipeline by framing extraction as a generation task. Now our system is built on these advances. The core components is the first one is the initial speech-to-text task, which we integrated the Whisper ASR model by OpenAI, the fine-tuned version of it actually, for robust voice transcription. And the second part, for the text-to-JSON conversion, we use two powerful instruction-tuned language models, FLAN-T5 and Gemma-3, both fine-tuned as well. Now, our key innovation and a major focus of our work is the integration of a Retrieval-Augmented Generation system, or RAG. This system leverages a vector database of menu items to provide crucial real-time context to the models, which significantly enhances the accuracy and robustness of the final JSON output. Now, what were our key contributions? While our work actually leverages existing state-of-art models, our primary contributions are in their novel application, integration, and rigorous empirical analysis. Specifically, our contributions are threefold. First, we constructed and are releasing a new large-scale dataset of multi-accent spoken restaurant orders. It features varied lengths and realistic background noise, and we believe it can serve as a valuable resource for future research in robust speech processing. Second, we designed and benchmarked a complete end-to-end pipeline that we call from voice to code. It is specifically tailored for the practical task of structured order processing and provides a strong baseline for future systems in this area. And finally, we conducted a rigorous comparative analysis of different model architectures. For example, FLAN-T5 versus Gemma-3. And importantly, different adaptation strategies, specifically Retrieval-Augmented Generation versus LoRa fine-tuning, which is the low-rank adaptation. This analysis provides the community with critical insights into the practical trade-offs of these modern techniques in a real-world, resource-aware context. Now let's start with the first contribution, the dataset. A core part of our work was involving the construction of a high-quality dataset to simulate realistic order-taking scenarios with variations in order length, item combination, speaker accents, and environmental noise. The process began with text generation. We designed a structured menu with 5 categories, 15 subcategories, and 48 distinct food items, with each item having an average of 3.92 potential customization, which is the matching of different items. We then developed a function to programmatically generate 4,200 unique valid order combinations. This followed a clear logic. First, we determined the order size, then randomly sampled main items, and finally assigning a random subset of valid predefined customizations for each item. This two-level sampling process ensured all generated orders were both diverse and logically valid. Next, we came into audio synthesis. To convert these texts into a diverse audio dataset, we used the Kokoro 82 million text-to-speech model, which is an open source one. We systematically synthesize each of the 4,200 texts using 10 distinct pre-selected speaker profiles to introduce crucial accent and gender diversity. This included 3 male and 3 female American voices and 2 male and 2 female British voices. This process resulted in a final clean dataset of 42,000 audio samples. Finally, we performed noise augmentation. To enhance the robustness of our models, we created an additional 42,000 noisy audio samples by adding 5 different types of realistic background noise to the original clean audio. These noises included ambient sounds, kitchen noises, live music, and people talking. Next, we have the system architecture, the figure. So this figure actually summarizes our proposed methodology. Let me zoom in a bit. The pipeline begins with a fine-tuned Whisper model converting the raw audio waveform into a transcribed text. This text then serves as the input to 2 parallel experimental pathways for JSON generation. Now, as you see, path 1 is the fine-tuning route. It utilizes a Gemma-3 model that is efficiently updated using low-rank adaptation, or LoRa. This path represents a strategy of internal knowledge adaptation, where the model's own parameters are efficiently modified to learn the task's specific patterns and vocabulary. Part 2 is the retrieval augmentation route. This path employs a FLAN-T5 model and exemplifies external knowledge augmentation. Here, the model is grounded with factual, real-time context retrieval from an external knowledge base at the moment of inference. This parallel design is essential for our research, as it allows us to directly compare these 2 distinct and powerful paradigms. The analysis is necessary to determine the most effective and resource-efficient strategies for deploying a robust and make it suitable for real-world systems, basically. Now, the first component was speech-to-text with Whisper from OpenAI. It served as our foundational pre-trained model. Now, to adapt this general-purpose model to our specific domain, we performed targeted fine-tuning on 6 distinct models. Each model was tailored to a different subset of our audio data based on 2 factors. The length of the orders, which we had them in 3 categories: small, medium, and large. Small being 2 to 4 items, medium being 5 to 7, and large being 8 to 10 items per order. And the acoustic environment, clean or noisy, as we mentioned before. Now, this granular approach was designed to optimize performance for varying complexities and real-world conditions. The primary objective during fine-tuning was to minimize both the word error rate, or WER, and the character error rate, CER. For training, we used key hyperparameters, including a learning rate of 10 to power minus 5, a batch size of 8 using gradient accumulation, and three training epochs. We also enabled mixed precision training for 16-bit precision, FP16, to optimize memory usage and speed on L4 GPUs used on these processes. The second component, text-to-JSON with LLMs. Once we have the transcribed text, the next step is to convert it into a strict JSON format. For this task, we evaluated Google's FLAN-T5 and Gemma-3 models to adapt these powerful base models to our specific task. We compared two distinct adaptation strategies. For the Gemma-3 models, we used LoRa fine-tuning, LoRa or low-rank adaptation. It's a parameter-efficient fine-tuning technique that significantly reduces the memory footprint and can accelerate the training process, as the data used in this research might be updated regularly. For our case study, it's a restaurant menu. So we thought that low-rank adaptation is a good way to go for real-world implementation. Now we implemented this with a rank of 16 and combined it with 4-bit quantization. The training was configured with a learning rate of 2 times 10 to power minus 4 and used the 8-bit AdamW optimizer. And for the FLAN-T5 models, we use Retrieval-Augmented Generation. Instead of changing the model's internal weights, this strategy provides the model with external contextual information at inference time to improve its accuracy. Now, if you allow, I want to give the stand to my co-author, Taha Khan, which contributed largely to the RAG part for the rest of the presentation. Thank you.
Hello, everyone. Can you hear me? Hello?
Yes.
Okay. So, yes, I worked mostly on the strategy B of our research, and my name is Taha Khan. So let's look closer at our RAG strategy. So we introduced retrieval-augmented generation to mitigate common LLM weaknesses. For example, hallucinations, where the model generates factually incorrect information. It usually used to happen with ChatGPT in the beginning stages. And it does this by grounding the generation process and in relevant retrieved documents. And in our approach, we used Pinecone as a vector database for its scalability and low query latency. We populated this database by embedding the query every menu item and its possible customizations using the FLAN-T5 encoder. And our RAG pipeline then operates in 2 stages. The first stage is the retrieval stage. Given a transcribed order, we can perform a vector search based on cosine similarity to retrieve the top K most relevant menu items from Pinecone. And then in the second stage, we used augmented generation, where we inserted these retrieved items directly into the prompt that is fed into our fine-tuned FLAN-T5 model. And this was providing additional context. So as the example on the slide that you can see in the green highlighted part, this provides critical context that anchors the output. And by incorporating the relevant menu items directly into the prompt, we significantly improved both syntactic and correctness and semantic accuracy. Can you go on to the next slide, please? So our first result, which is about Whisper transcription accuracy. Beginning with Whisper models, this table summarizes the character error rate and word error rate for our 6 fine-tuned models. The results showed a very clear trend. The models achieved extremely low error rates on clean audio for both small and medium length orders. The best performing model trained on small clean orders achieved a character error rate of about 0.05% and a word error rate of 0.16%. But this performance degraded significantly as the orders became longer, and there were like 10 items per order, or when the noise was introduced. And on large noisy orders, the word error rate was around 5.48%. And I believe this is a key finding, as it highlights the importance of addressing both order complexity and acoustic interference in real-world voice-to-text applications. And this also shows that ASR stage can become a critical bottleneck. And the second result, which is where we introduced Retrieval-Augmented Generation, and this was a game changer for smaller models. And we evaluated the FLAN-T5 models on the text-to-JSON task without any external context. Performance scaled with model size as expected. The largest model, FLAN-T5 large, performed exceptionally well, achieving over 98% accuracy on large orders. In contrast to FLAN-T5 small, it struggled a lot, achieving only 30.12% on the same dataset. However, when we integrated RAG pipeline, the results changed dramatically. This table shows the accuracy scores on large orders, both with and without RAG. The improvement is most significant for smaller models like FLAN-T5 small. Its accuracy jumped by nearly 24% percentage from 30 to 54%. Similarly, FLAN-T5 base saw a 21-point improvement, going from 66 to 87%. And this clearly demonstrates that RAG is a highly practical enhancement that can make smaller, more efficient models viable for production in resource-constrained settings. And our third result was generalization and recommendation. We also conducted an extensive evaluation of Gemma-3 models, comparing full 16-bit fine-tuning against the more efficient 4-bit LoRa versions. The results showed that LoRa quantization offers a strong balance of efficiency and accuracy through performance, though performance can drop for smaller models on the most complex inputs. And to test the robustness, we conducted a comprehensive cross-dataset validation where we trained models on one order length and tested them on others. And a key finding here was that models trained on medium length orders consistently yielded the most balanced and generalizable for performance across all test sets. And models trained only on large orders often struggled when tested on small ones, reinforcing the challenge of adapting from long to short sequences. And based on all these findings, we offer these practical recommendations. Firstly, to prioritize maximum accuracy, and if computational resources are not a concern, FLAN-T5 large is the top performer, no doubt, and it achieved near perfect scores and generalizing extremely well. But for a balance of efficiency and performance, FLAN-T5 base with RAG is an excellent choice. The 4B small 4-bit Gemma-3 model also offers highly competitive performance while being very lightweight. And as 4-bit models deliver near parity performance at a fraction of the resource cost, both are highly suitable for the production environment where model size and inference speed matters. Next slide, please. So in conclusion, in this work, we developed and evaluated an end-to-end pipeline for converting multi-accent spoken orders into structured JSON data. And a challenging task with significant real-world applicability is that our central contribution is the demonstration that while massive models like FLAN-T5 large provide state-of-the-art accuracy, more efficient and practical solutions, including RAG-enhanced and RAG-enhanced models and LoRa quantized Gemma models can achieve highly competitive performance. Our experiments yielded several key insights for the NLP community. First, we identified that the fine-tuned Whisper ASR model can be a critical bottleneck as its performance degrades significantly on long and complex orders, leading to error propagation. And secondly, our results quantitatively prove that Retrieval-Augmented Generation provides a substantial performance boost to smaller language models, making them viable for production environments where they might otherwise fail. And lastly, our cross-validation analysis provides a clear recommendation that training on a diverse distribution of medium-length orders leads to the most robust and generalizable models for this task. And for future work, we will focus on expanding our experimental validation, as this was suggested by our reviewers. Our key directions are firstly that we want to test the pipeline on real-world conversational data, moving beyond our synthesized data set. Secondly, exploring a wider variety of acoustic conditions, and this is to further push the boundaries of model robustness. And finally, we were thinking about developing more sophisticated, semantically aware evaluation metrics for verifying the correctness of structured JSON output. And this would help going beyond simple string similarity. Well,
Thank you, Dr. Taha. So if you have any questions, thank you for listening, first of all. If there's any questions to me or Dr. Taha, we will be glad to answer those.